Temperature. So we've talked about solid matter and how the particles are still moving, right? Atoms and molecules in matter are always moving, some more than others. That constant random motion is thermal energy. It is a form of kinetic energy. Temperature is not the same thing as thermal energy, but they are related. The temperature is a measure of the thermal energy. So temperature is a measure of thermal energy. The hotter the object is, the greater the random motion of the atoms and molecules. So more motion in the particles, higher temperature. What do you think the atoms in the air outside are doing right now? They have high kinetic energy? Yeah. Does anybody know what is the current temperature? It's supposed to get up to 111 today. Just curious.
Is it 110 or something?
Well, let's see. Wonderground says it's only 98 right now. Headed for 110. High temperature is a measure of the kinetic energy, the thermal kinetic energy. So outside where it's 98 degrees, the particles are moving faster. So how do you remember that particles moving faster means hotter? Well, I think about barefoot people on the beach. Did you know that Reedley has a beach?
No.
Actually, right now it doesn't. It's all underwater. It's on the river. Yeah. It is this big, big sandy area when it's not flooded. On a day like today, if it wasn't underwater, would you be strolling on that sand barefoot? No. That sand would be burning your feet, right? So how would you get from the parking lot to the water? You'd run with sandals, yeah. That's what a smart person would do. Let's say we had no sandals. In a fictional world where there were no shoes of any sort, you'd have to run, you'd hot-foot it, right? So when the ground is hot, people move quickly who are barefoot. You go to Pismo today, I don't know, but usually Pismo's overcast and windy and cold. And people in the Central Valley go to Pismo to get cold, right? We got to get out of this heat and we want to go sit and shiver on the beach, right? So the sand there is cold, so you can walk real slowly and not burn your feet, okay? So particle motion, moving faster, higher temperature, higher kinetic energy, higher thermal energy. I want to go to Pismo. Okay, so the difference between temperature and heat. So heat is the transfer or exchange of thermal energy that's caused by a temperature difference. So heat has units of energy. You take a piece of cold ice and you drop it into a cup of warm water. What happens? The water gets colder and the ice melts and then becomes warmer until they get to the same temperature, and then nothing really happens, right? Energy will flow from high temperature to low temperature. Never do you have it happen that you stick an ice cube in there and you grow more ice cubes and the water starts boiling. It doesn't happen because it flows to the same level that energy does. Temperature is a measure of the thermal energy. Heat is a transfer or exchange of that thermal energy. So heat has units of energy. Temperature has units like degrees Celsius or degrees Fahrenheit. So to measure temperature, we generally use a thermometer. Thermometers work because the liquid in them will expand somewhat in response to temperature. So as the temperature goes up, the liquid expands and we see it rise in the glass tube. There are three main temperature scales, Fahrenheit, Celsius, and Kelvin. So Fahrenheit is what the weatherman reports the temperature in outside, 98 degrees Fahrenheit. Room temperature is about 72. It's just a good idea to have some point of reference for these different temperatures. The Celsius scale On that scale, room temperature is about 22 degrees Celsius. The really big difference between these, Fahrenheit and Celsius, has to do with the freezing point of water. The Fahrenheit scale has a history behind it. There are reasons for its weird numbers. Water freezes, pure water, at 32 degrees Fahrenheit, and it boils at 212 degrees Fahrenheit. Where did those numbers come from? Well, there's a story. I'm not going to tell you that story. We don't have time for that. The Celsius scale is the metric temperature scale. And so they assigned 0 to the freezing point of water, and they assigned 100 to the boiling point of water. That makes a little more sense, doesn't it? And then there's 100 degrees in between. On the Fahrenheit scale, there's 180 degrees in between. And so a Fahrenheit degree and a Celsius degree are not the same size. And 0 is not in the same place. And then there's this Kelvin scale, which we'll need when we talk about gases. This is related to the Celsius scale. There are still 100 degrees, or 100 divisions, between the boiling point and freezing point of water. But on the Kelvin scale, 0 is set at absolute 0. It is the lowest theoretically possible temperature, the temperature at which all movement of atoms stops, not even wiggling. Just absolutely stopped. So a friend told me a joke. He said, did you know that you can lower your body temperature to minus 273.15 degrees Celsius and still be okay? Okay. 0 Kelvin? I like that one. So it does look like okay. So the difference between Celsius and Kelvin is just this number, 273.15. The size of the degree and a Kelvin, they're not degrees Kelvin, they're just Kelvins. The size of the unit is the same, but 0 is in a different place. So we need to be able to convert between Fahrenheit, Celsius, and Kelvin temperatures. We cannot do this using dimensional analysis because the 0 places are different. And so there's adding or subtracting involved. So we have to use an equation. So I will give you these equations on the midterm exams. It will not be given to you on the final exam because that's a standardized exam and they don't give you much of anything. So you'll have some time to use these and get used to them. So those are the equations to convert back and forth. This one is pretty easy. Once you get that 273 number in your head, Kelvin and Celsius, you just add or subtract 273. If you ever get a negative Kelvin temperature, you did something backwards because negative is impossible on the Kelvin scale. You can't go lower than absolute 0. That's why it's absolute 0. It's the lowest. So let's do this. Convert 358 Kelvin to Celsius. Well, we need an equation. We're trying to find Celsius, and so we want to know C equals something. So we look at the equations that we have available. We've got these two. Well, this degrees Celsius equals degrees Fahrenheit. No, that's not going to work. This one says Kelvin equals, and here's degrees Celsius. So this equation is going to work, but we're going to have to rearrange it. So the equation is Kelvin equals degrees Celsius plus 273.15. I want to know what degrees Celsius is. This is the type of rearranging that we shouldn't have to think about. But when we do start thinking about it, then it just becomes really, really hard. So just try not to think too much about this. I'm just going to subtract 273.15 on both sides. And so I get degrees Celsius equals Kelvin minus 273. So my Kelvin temperature was 358. 358 Kelvin minus 273.15.
Would it have been wrong if you look at 358 in SK and then just subtract 273 from it?
You can, as long as you get 358 minus the 273, I don't really care how you get there. Yeah, because this is one where, I mean, Kelvin equals this plus that, and so you know, it's like 358 equals what plus 273? If I have, well, anyway, so the calculator says 84.85. When you're doing these things with the equation, leave the units out and just tack them on at the end. This is degrees Celsius. So any questions about how I got to the number? Yeah.
Where'd you get the 358 from?
That was right here.
Oh.
That's okay. I bet there was at least one other person that were like, where'd the 358 come from? Yeah, that was, I should have written that down first. That's what we're asked to do, convert this to Celsius. It's okay. My husband calls that a brain fart. Your brain just goes hiccup and what happened there? Yes?
So when you're doing the sig figs, that doesn't matter?
That's a good question. When you're doing this, do the sig figs not matter? Sig figs always matter. Okay, so what do we do about sig figs? Yeah, so this one isn't too hard to think about because it's just subtracting. And so we're looking for fewest number of decimal places. And so this has no decimal places and this has 2 decimal places. And so we should round this to no decimal places. So we should round this here and say that it's 85 degrees Celsius. When we do Celsius Fahrenheit conversions, there's multiplication or division and adding or subtracting in there, and things get a little messy. We don't actually have to deal with all of that. So this is the shortcut. Look at the starting temperature. This is to the nearest 1, right? The last digit is in the ones place. I want to round my converted temperature to the same place, the ones place. If this was to 0.0, if it had 1 decimal place, I'd round this to 1 decimal place. So just whatever your starting number is, do the whole calculation and then round to the same place. The reason that works is that a Kelvin and a degree Celsius are exactly the same size, and a degree Fahrenheit is less than twice smaller than those, and so it doesn't really matter. We're just moving the 0 around, basically. Let's do another one. Convert 139 degrees Celsius to Fahrenheit. So we've got 139, I'll write it down this time. 139 degrees Celsius, and we want to go to Fahrenheit. We have to use an equation. So let's find the equation. So this is what I've got. Degrees Celsius equals degrees Fahrenheit minus 32 divided by 1.8.
Well, we need to memorize the Fahrenheit one for the final two.
I don't remember if there are any questions specifically asking you to do this conversion. I suspect that there are not. But it wouldn't hurt to memorize it. So there's the equation that I have available to me. I want an equation that says Fahrenheit equals something. Fahrenheit's over in here. When you need to rearrange an equation, do it before you stick numbers in, because once you put the numbers in, things can get really messy. So it's better to do it when you've just got letters. So this is challenging for some students. So I want to get rid of this 1.8 over here. So if I multiply both sides by 1.8, the thing about an equation is it's an equality, right? Each side is the same as the other. It's like a balancing on a teeter-totter. And it has to stay equal. So if I do something to one side, I have to do the same thing to the other side. So multiplying by 1.8, why did I want to do that? Because 1.8 divided by 1.8 is 1. Those cancel out. So now what I've got is 1.8 times the temperature in degrees Celsius equals degrees Fahrenheit minus 32. So now what I need to do is add 32 to both sides. So after dealing with that mess, the degrees Fahrenheit is going to be 1.8 times the Celsius temperature plus 32. So now I can take this temperature in Celsius, 139. I'm going to multiply by 1.8 and then add 32. So 1.8 times 139, enter, plus 32. 282.2 is what my calculator says, and that's degrees Fahrenheit. Now sig figs. The original temperature was to the nearest 1, and so I want to round this to the same place. So I'm going to say 282 Fahrenheit. Yes?
Since there was division as well, let's say it was like 139.0, would you use sig figs to determine it, or that's
I would always just go with the number of places in the original number. So if this was 139.00, the answer on my calculator is going to come out the same, right? But then I should, if this was to the nearest 0.01, then this needs to be to the nearest 0.01. If this has 2 decimal places, then this should have 2 decimal places. And so I would say it's 282.20 degrees Fahrenheit. This is, for temperature, doing it this way, not only is it simpler, but it's actually more accurate than actually looking at the sig figs, because there's some funny things that can happen with the sig figs. Convert minus 321 degrees Fahrenheit to kelvins. So minus 321 degrees Fahrenheit, and we're asked to get to kelvins. Didn't give you an equation between Fahrenheit and Kelvin. We're going to have to use 2 equations. We're going to have to convert Fahrenheit to Celsius and then convert Celsius to Kelvin. So we can't just string these together with dimensional analysis because of the relationships being complicated. I want to find degrees Celsius. So degrees Celsius is degrees Fahrenheit minus 32, the quantity divided by 1.8. By the way, if you're wanting to do the full-blown sig figs with this, the 32 and the 1.8 are exact numbers. So I put my number in here, negative 321, and I'm going to subtract 32 and divide by 1.8. Be careful when you do this on your calculator that you finish the subtraction before you divide. Otherwise, you'll end up with something else. And be careful of that negative sign. So I'm going to put in my calculator the negative sign, not subtracting, but the negative change sign thing. Negative 321 minus 32. You could use parentheses if you want. And then I'm going to press equals, tell my calculator, finish that. And then I'm going to divide by 1.8. And my calculator says minus 196.1111. It goes on and on and on. Degrees Celsius. I'm not going to worry about sig figs yet. I'm going to keep some of those ones, and now I'm going to take that number, and I'm going to convert it to Kelvin, and I'm going to round at the end. Kelvin equals degrees Celsius plus 273.15. So I've got that number, negative 196.111111, whatever, plus 273.15. And the calculator says 77.038888, a whole bunch of eights. And that would be Kelvin, not degrees Kelvin, just capital K. Now, significant figures. My original number was the uncertain digit was the ones place. So then here I'm going to round this to the ones place. And this is going to be 77 Kelvin. Any questions? There's a lot of practice in converting temperatures on worksheet 2B.